Hi everybody, welcome to another up-to-date DWF repair video. It's the arcade season again. I've been sent for repair a number of PCBs made by the Italian Zaccaria company. This is an Astro Wars game PCB. Someone else already tried to repair this one, it seems. These games have a separate sound PCB. I've also been sent the original EPROMs that were substituted for some reasons. Then I've also got the switch harness, we'll see later why. As I always do when working on repair like this, I start by checking all diode and transistor junctions with a multimeter. This is also a good occasion to look around for weird or unusual things and maybe to spot potential problems before applying power for the first time. For example, it was really obvious that someone else already substituted a good number of ICs on this PCB, not only because some of them are socketed, but also because the date codes are not matching the 1980 date of the original ICs. In this example, we see a 1983 IC that has been replaced without a socket. I found quite a few more substituted ICs that have been just soldered back without a socket. This is, in my opinion, a very bad habit that has no real excuses. The second check I usually do is measuring the ESR of electrolytic capacitors to find any possible bad one. In this board, all of them looked still good. Zacccaria arcade PCB were a bit unusual. They have, for example, no PCB edge connectors. They used different other types. In this picture we see the power input connector solder joints that look very messed up in this case. So first of all I've cleaned the old flux residues and applied new tin to all the pins. Also the joints on the other side of the PCB didn't look too good. So I've resoldered the ones that connect to actual traces on the top side of the PCB. I've then decided to check the two substituted EPROMs against the original ones. On the first one I found a difference of 2 bytes, and on the other one only 1 byte was different. The substituted EPROMs contain the images used for the MAME emulation. I think the original ones might be a slightly different ROM set. However, I've decided to check these dumps on the emulator, just to see if they cause an early crash or corruption. Unfortunately, I have 0 skills on this old arcade, so all I could do is verify that the first wave and the second one seem working. So I decided to keep the original EPROMs for the moment. It's now time to wire a power supply and power up the board. The wiring diagram from the service manual shows the various connectors pinouts. I'm not sure I've got the actual connectors used in the cabinet or just some other ones that are correct match. Wire colors seem just kind of random. Notice for example a ground wire with a red color, which is really the last color anyone would use for a ground wire. I'm using an old PC power supply to test this board, by the way. And here we have more wire color madness. Of course, I've verified more than 2 times every connection I made against the actual supply pins on the various integrated circuits. A power supply wiring error could be catastrophic. The inputs, audio and video connectors can be mated with regular pin strips, so I plan to solder wires to the pin strips to connect the audio PCB when I need to test it. So I'm going to solder wires to this pin strip to connect the RGB video output to the monitor. I didn't have a shorter pin strip for this one, by the way. Like many other Italian-made arcade games of that era, this one uses negative video signals, so colors would be initially wrong. But I plan to make a video inverter so I can fully check this board color outputs before shipping it back. It seems there is an image, but synchronism is bad or missing entirely. I started looking at the video output circuit on the schematic, and I soon realized that I'd made a wiring mistake. I connected my sync wire to pin 2 instead of pin 1, which is the correct one. I've also noticed that the sync signal is actually a composite black and white video output, so I'll probably use this one to troubleshoot this board until I make the video inverter circuit. However, after correcting the video connection, all we get is a static fan image. These Zaccaria arcade, as I said before, are unusual. Unlike most of the other arcade games of the same year that were using CPUs like the MOS 6502 or the Zilog Z80, or at the very least the Intel 8080, these are based on the quite uncommon Psygnetics S2650 8-bit CPU. For sure, it's the first time I see a real 2650 in my life. The 2650 is, of course, well documented. Like most CPUs of the 1970s, this one has an 8-bit data bus, a 15 bits address bus, a few bus control signals pins for memory and I/O read and write, interrupt request pins, a reset input and a clock input, plus other pins that for the moment we can ignore. As for all other CPUs, the first 2 things to check are a proper reset pulse at power on and a proper clock signal. Notice that the reset input on the 2650 is active high, unlike, for example, the 6502 and Z80 ones that are active low. It means that the logic probe must show a high blink at power on, then indicate a logic low for the rest of the time. A clock signal must be present on pin 38 of the CPU. And it looks fine. The next thing we want to check usually are the CPU address buffers that in this case are made with a bunch of AND gates. Usually I install an op generator to have a known good pattern to execute this test, but I haven't made one for the 2650 CPU, so I've just checked each gate output to see if it's toggling or it's maybe stuck, and no stuck outputs were found. Then it's time to look at the address decoding logic. As before, this would be best done with an op generator, but at first we will check if any of the outputs looks bad in some ways. And indeed, when looking at pin 4 of both 5H and 5I integrated circuits, we get this bad signal that's not going correctly to the 0 level. Now, this looked like a drag conflict. The HP current tracer showed high current on both 5H and 5I pin 4, that, as you see on the schematic, are connected together, but no high current on pin 3 of 1I, that's an input connected to the same line. However, this line also goes to other pages of the schematics named as the SAM signal. Looking at the other pages, I found that the signal also goes to pin 1 of both 4F and 5F integrated circuits, but the probe showed no high current also on both these inputs. So I've decided to cut pin 4 on both 5H and 5I. And now the signal looks correct. I think I know what's going on here. When probing around 5H and 5I, I've noticed their strange marking, but at first I didn't really pay much attention to them. Then I've realized they must be for sure replacement ICs. In fact, they are an East Germany TTL series that was for sure not available in the 1980s in Italy. So a DL155D is actually a replacement for a 74LS155, but is that what we need? The schematic clearly indicates 156 for 5H and 5I and not 155. So let's look at the datasheet. The only difference between the 155 and 156 is the output type. The 155 has totem pole outputs, which means they will either be grounded through an NPN transistor or they are internally pulled up to VCC through a series of a resistor, a transistor and a diode. Instead, an open collector output, as its name suggests, is just an NPN collector that can only be grounded or remain floating. In this way, more than one output can drive the same line. Totem pole outputs cannot be paralleled to drive the same line. On the schematics, we can see clearly that A, B and C outputs are driven together by the two ICs, so clearly they must have open collector outputs or they will be always fighting against each other. Notice also that every output has a pull-up resistor to VCC, which is typical when using open collector outputs. And yes, both the ICs were replaced. Look at the solder joints. The original ones here are clearly different. Unfortunately, the 74LS156 is enough uncommon that I didn't have two spares in my parts, so I had to order a few ones and wait for them to arrive. Then I've removed the wrong replacement ICs, soldered two sockets and installed two 74LS156 that are now the correct kind of IC in these positions. Let's power on. Well, now the CPU can draw the battlefield, but seems it gets stuck. And every time I reset the CPU, it seems halting on a different point. So I've tried to clean the ROM pins and reseated them on the sockets. And now it goes happily into the attract mode. Of course, the colors are still inverted. Now, for all the tests, I'm going to use the black and white video output that looks much better than the inverted colors. So far so good, the CPU board looks stable. As I said, Zaccaria arcades are unusual. For example, all the game inputs require some diodes. That's because all the inputs and the PCB dip switches are scanned in a matrix-like circuit to save input ports probably. So, to test the input actions, I'll use some diodes and wires in the appropriate pins of the input connector. I cannot easily use the switch harness that I got together with the boards because it is made to plug into a different board and the connector doesn't match the CPU board's one. Here I will test both the coin inputs. The first coin input is working. Of course, with a wire I'm getting a lot of bounces. The second input works too. It went from 5 to 8 credits. Now I started a two-player game by hitting the diode into the appropriate input pin. Let's now start a one-player game. And test the left and right inputs. And both worked fine. The last input to check is the fire one. And that's working too. These arcade games have a separate sound generator and amplifier PCB. In the wiring diagram we can see that the sound board is connected with an 8-wire interface to the CPU board and a separate connector for power input and the speaker. So I've made a quick interconnection cable with a couple of pin headers. Let's coin up. And start a game. Well, it seems okay, but this game is not playable without a proper input console. As I said at the beginning, the RGB video output of this game is inverted. It means that the black lever is the most positive voltage on each color output, and the brighter a pixel needs to be, the lower the voltage will go. This can be seen on this part of the schematic. Notice that each color signal has a pull-up resistor to VCC, and all the various image components drive the color lines with 7406 ICs that have open collector outputs. So when nothing is displayed, the color signal will idle at 5 volts, and the 7406 can only drive their output low. So whenever something is displayed, the signal gets lower than 5 volts by some factor that depends on the various resistor values that are in series with each 7406 output pin. However, to display correctly the image on my monitor, I will need the black lever to be the most negative voltage of each color output. So I've drawn this simple circuit that can do the polarity inversion on each color output. Q1 is a common emitter amplifier with a voltage gain of 2. Common emitter amplifiers have also the property to invert the signal from input to output, which is exactly what we want. Q2 is a common collector current buffer, also known as an emitter for lower. It will just replicate its input signal at its output, providing enough current to drive the 75 ohms video input. Having another 75 ohms resistor at the follower output will ensure we drive the video cable with the correct impedance, and the resulting signal voltage will also be divided by 2, compensating the first amplifier voltage gain. I've quickly simulated these circuits in LT-Spice to tweak some resistor values. Then I decided to build first one channel only into a piece of unetched PCB, where I glued other small pieces of PCB to make insulated islands and solder the various components. And here we see the result of the video inversion applied to only the blue output. It looks good enough, so I'll build two other identical circuits for the red and green outputs. Well, the funnel board looks a bit too crowded. I have underestimated a bit the size of the board, it seems, but in the end I could fit every component needed for the 3-signal inverters. Let's see what happens. Yeah, it looks good. This would be very useful since I'm going to service more Zaccaria arcades with the same kind of video output. The brightness levels also seems very good. So I hope this was an interesting repair video and that you learned something. If you have any question, please use the comment section below. It's all for now. Have a nice time and thank you for watching.